So the section is optical properties of materials. If we want to understand how light interacts with materials, if we want to make use in some engineering sense of light or laser light, we have to have some basic idea of how the light will interact with various types of materials, and therefore we need to know something about their optical properties. We're going to break these down into two very broad classes, insulators and metals. We'll see that the optical properties of metals are similar to insulators, but they have one additional complication, and that is related to the nature of the refractive index. So the refractive index, or the index of refraction, is really just a measure of how fast light can travel through any particular material. So it's the ratio of the speed of light in vacuum to the speed of light in that particular material, and is usually given the symbol n. We saw from Maxwell's equations that the electric permittivity and the magnetic permittivity, permeability is related to the speed of the magnetic electromagnetic wave. And so if we're defining a refractive index as being the speed of light in vacuum divided by the speed of light in the material, then that gives us a relationship between the electric permittivity and the magnetic permeability in the material and in vacuum. In terms of the relative permeability, remember, is just a constant, so that epsilon is equal to that constant kappa E times epsilon naught, where epsilon naught is the permittivity of free space, or the vacuum. Then we can see that the refractive index is related to the product of these relative permittivity and permeabilities. We've also seen from Maxwell's equations that we can pretty much ignore the magnetic properties of optical materials. That's not going to be true when we come to magnetic materials, obviously, metals. But for the moment, for optical materials like glass, plastics, and so on, liquids, then the refractive index is roughly equal to the square root of kappa E. Now, this is a very, very gross simplification, and that equation 4, only works well for very simple molecules that are simple gases, elemental gases. In general, the permittivity and the relative permittivity and the refractive index are frequency dependent. In other words, as we go to from red light through to blue light, then the value of the refractive index will be different for those wavelengths. Let's look at how good the theory is. So here are some materials, gases, liquids, and solids. And here is the value of the square root of kappa E. And here's the actual value of the refractive index. You can see that for simple molecular gases, then we have a fairly reasonably good agreement. As we get to denser materials, then not so good. Benzene again is relatively simple. Water you would think would be the most simple, but water is a very strange material. It behaves in very strange ways. When you cool it down, when you freeze it, it gets bigger than its liquid state, things like that. And then you'll see gradually, we're getting better or worse approximations between these two. One thing to note, though, is that the value for the electric permittivity, or the relative permittivity, is measured at 60 Hertz. Okay. Whereas the refractive index is measured using sodium light, yellow light. It's the same as the street lights. And that's at 10 to the 15 Hertz. or 10 to the 14 hertz. So if you measure something at 10 to the 14, 15 hertz, and also at maybe 10 hertz, would you expect it to behave in exactly the same way and give you the same result? Almost certainly not. And so it's quite remarkable, actually, that these have any sort of agreement at all, given the massive difference in the frequencies at which they've been measured. The fact that they're the same orders of magnitude tells you that the simplification that we've got works actually not too bad.